Welcome back again. Today we'll try to do something different. We'll try to have fun with quantum, and in particular we'll be discussing a little bit of quantum games. We will start by reviewing a little bit of what we've seen in the past lecture on quantum algorithm, and then we will get into quantum battleship. You should take this lecture as an invite to be creative with quantum mechanics. Now, quantum algorithms, there are different classes of quantum algorithms that reach quantum advantages. And we've seen quantum algorithm based on quantum search. We will be discussing in the next module algorithms based in quantum Fourier transform, and also some other way to get in quantum advantages via simulating quantum mechanical system with quantum simulation, for example, for chemistry application. There's a lot of research done in this area, and it's all very well documented and categorized in this website, quantumalgorithmzoo.org. So I invite you to take a look at it and see if you find your favorite quantum algorithm and if quantum mechanics can help out for your favorite problem. But there is other ways of using quantum mechanics, and in particular, today we will be discussing how to be creative with quantum. This is an open question of what else we can use quantum mechanics for. And today we will be discussing quantum games. Now, quantum games are games that are partially run on a classical computer, but also have part of the game that runs on actually on quantum hardware. There are a lot of quantum games, and many of them, they are documented very well in James Wooten website, decodocu.medium.com. Now, some of the features of quantum mechanics that you can use for quantum games are, for example, the superposition principle that we'll be discussing. When you have a state 0, you can Hadamard it, and you can get a state plus. That is a superposition of 0 and 1. Now, if you measure it, then you collapse into the 0 state 50% of the time, and other 50% of the time you collapse to the state 1. This you can use as, for example, a random number generator for a game. Another feature that is very useful for, that can be very useful for quantum games is entanglement. This can be seen by this very small circuit where we Hadamard the first qubit, and then we apply a C0 with a second qubit, always in this, also in the state 0. If we do that, the resulting state will be a coherent superposition of the 0, 0 and 1, 1 state. This is a very interesting entangled state that is not decomposable into the tensor product of a state of the first qubit and a state of the second qubit. And this can be actually very interesting because it can pertain certain correlation independently of whether the qubits are close by or not. So let's see an example of a quantum game. Today we'll be discussing a game of battleship. We can take a grid that we see over here, and what we need to do is to identify each of the square in the grid with a qubit. You have a ship that is 1 qubit, and it occupies one of the square, and it takes the state 0 if it's intact, and the state 1 if it's completely destroyed. Now, in this version of Battleship, there are 3 types of ships. The first one can be destroyed by a single bomb. The second one can be destroyed by 2 bombs, while the third one is destroyed by 3 bombs. Now, this we can code by considering that when we hit the first ship, we apply an X gate that flips the state 0 into a state 1. To be destroyed by 2 bombs, it means that we need to apply the X gate. We need to apply a gate 2 times to destroy it. So what we will apply is the root of X gate. Likewise, for 3 bomb, we apply the root 3 of the X gate to destroy the ship. So now let's play. The first player places the ships. For example, we place it in this way. The second player attempts to destroy the ship. So let's try out. We hit the ship that is supposed to go down with two hits. What this does is that what this means is that we apply a root of X gate to the state 0 of the originally intact ship. What happens then is that by applying the root of X gate, which explicitly can be written in this form, it means that the ship now is in a coherent superposition of being half destroyed and half intact. Now let's try again. We hit again the same place. And then we apply another root of x gate to the ship. This destroys completely the ship and brings the state from 0 to 1. We now need to be very careful, because if we hit it again, then what we do is that we apply a root of x gate to a state 1. And this means that actually we try to resurrect the ship, because now we have a 50% probability of having synced the ship and having the ship intact. So quantum games can actually be very interesting, because you can add different level, and you can even resurrect battleships. Now this is a very simple version of quantum battleship. There are many other versions. Other versions can also include longer ships, and for longer ship you can include more qubits. For example, another version of quantum battleship can have ships that are two qubits long. And then we can have different level of intact, damaged, more damaged, or destroyed type of ship. And then we can even apply some very interesting gate, like the control Z gate, that will create some superposition state of completely intact and completely destroyed ship. This is just one of many combinations of the ship state, but also of the quantum battleship version. And this is only one out of many quantum games that one can get. There are other famous examples of quantum games, are for example quantum tic-tac-toe, quantum chess, space moth. And what I want to encourage you is to be creative and make your own.